Hey guys, in this video I'm going to talk about the Gompertz curve or the Gompertz function. So I'm going to go over what the function is and what the parameters are in the model, and then I'm going to talk about fitting a Gompertz growth curve model in R and how you do that using nonlinear regression. Before we get into the demo, let me go ahead and write out what the formula for the Gompertz curve is. So it's a function f of t is equal to a times e to the negative b times e to the negative ct. So it's a double exponential function with three parameters, a, b, and c. And these three parameters stand for a is an asymptote, so it's a horizontal asymptote, or if you're thinking about this in terms of a growth curve model, so this could be the growth of a population f of t at a certain time, then you can think of the asymptote as the carrying capacity of the system. Then b is going to be the displacement on the x-axis, and c is going to be the growth rate. So similar to models like a logistic model, which is used for modeling like human population growth, this model is also used for modeling limited population growth. It's also sigmoidal, similar to the logistic regression. Actually, the logistic and the Gompertz curves both belong to a family of like generalized logistic functions called Richards curves. And the main difference between a Gompertz curve and a regular logistic curve is that for a logistic curve, as the population increases, the growth rate linearly decreases, but in a Gompertz curve, as the population increases, the growth rate exponentially decreases. So the growth rate changes exponentially here, and in a logistic it changes linearly. And so this model is commonly used as a population growth model for tumor cells. So let me switch over to a paper. So this is the paper I was talking about. It's called Dynamics of Tumor Growth, and I'll put it in the description box below. It's freely available online. And this was the first paper to use the Gompertz curve to model tumor growth, which is a very commonly, it's like a very well-known growth model for tumor cells after this paper. And basically this paper, I skimmed through it, it said that tumor cells were initially thought to grow exponentially, and they were thought to grow exponentially with maybe a limit or an asymptote depending on the nutrients that was available to the cell or that would be available to the cell. But this paper said instead that the growth rate of tumor cells much more closely follows a Gompertz curve. So I'm going to do an example with tumor cells in this video, and I got the tumor cells, I'll put a link to this in the description box below as well, but I got the data of tumor cell volumes from this random website. So this is a data set attached to a book. I don't actually have the book, I just randomly Googled for tumor cell volume data, but I'll put a link in the description box below if you guys also want to download the data set that I'm working on. And so now let me go to R and actually do the demo. Okay, so I have my R code here, and I'll also try to link this or upload this and put in the description box as well. So the first thing is I'm just setting the working directory and finding the data. The data set, I'm not completely sure of like the context of this because I don't have the textbook that goes with the data, and the data sets don't come with a description. So I'm not exactly sure what tumor type of cell this is, but as you can see, the data set comes with 590 observations and 4 variables. So the variables of interest for us are the days. So this is our time t, and then it has recordings of the volume of a tumor cell. And I believe the volume is recorded as what's called a spheroid. So that's how you calculate the volume of a tumor from what I've read. And the original data set gives it in volumes of natural log of a tumor volume. So I just wanted the original tumor volume. So what I did was I converted the log back to its original just by taking the exponent, and I added that to the data set. So I converted from the natural log to get back to the regular tumor volume. And if you look at the data set, there's a column for ID, and this seems to ID different types of tumor cells that were measured. So they analyzed the growth of tumor cells over time for different tumor cells. So another thing I wanted to do with the data set was just get one of the tumor cells. So I wanted a curve just for one tumor cell. So the code that I just ran to plot the data, this plots all the different types of tumor cells. So you can see they appear to have basically different types of growth rates. And so I just want to model one growth rate, and also there seem to be some outliers. So the next part of the code, I removed the outliers. I said, I think anything over like 1,000 or something, or 1,200, to remove that data as an outlier. And also I said just to get like one group of tumor cells. So after I remove the outliers and subset for just one tumor cell growth, then I'm going to replot the data. And when I replot the data, it shows me now the growth of one tumor cell. So it shows me the volume plotted over time. So time is the x-axis in days, and this is the spheroid growth in volume over time. So this is what we want to fit a Gompertz model to. So basically what I wanted to do is a regression. So I wanted to regress the growth or the size and volume on time. And from the function that I showed you in the beginning of the video, you saw that the function is a double exponent. So not only is it not linear, it's not even exponential, it's doubly exponential. If I wanted to do this type of model, this is what's called a nonlinear regression problem, because the parameters are not a linear combination for the y or the f of t. So to do that in R, I'm going to load in this library called EasyNLS. So it basically fits nonlinear regression models. Also in this video, I wanted to fit the model first as an exponential model, just because in the paper it said that people used to think that tumor cell growth was exponential up to a certain asymptote when the cell ran out of nutrients. So I wanted to first fit it using the exponential model just to show that it's not a good fit for the data. And when you're fitting a nonlinear regression model, it's different from linear regression, because when you're trying to estimate your parameter values, which the Gompertz model has 3 parameters, A, B, and C, there's no closed form solution for most nonlinear regression problems. So you have to do basically like numerical approximations. So with estimating the parameters, you have to input usually like some starting values, and then using an optimization algorithm, a computer will give you better estimates. So you have to do that for both an exponential model and for the Gompertz model. For the exponential model, there are just 2 parameters, A and B. So this looks like it's maybe the starting value, and then this is the growth rate. B would be the growth rate. So I just fit the model, and for this code, the nonlinear sFit will fit the model to my data. Model 6 means to fit it as an exponent, and then start gives you the starting values. So I did that, and then this gives me an exponential model, so A times e to the bx, and then this gives me my final estimates for the parameters. So for the parameter A, the final estimate was 120, and for the growth rate, the estimate was 0.008. And now the next part, I'm going to fit that exponential model to the data and plot it as a curve. When I do that, you get this. So this is the actual data, the red dots, and then this is what the exponential model would look like. And here it says that the r squared, or the variance explained in the model, is 0.32, you can say. So it's not very good. You can see that literally almost none of the points fall anywhere near this line. So this doesn't seem to be capturing the growth rate of the tumor volumes very well. Next, I tried fitting it with a Gompertz model. So in NLS Fit, the Gompertz model is model number 10, and the starting values, I did it based on what the plots of the observations look like. So to get starting values, A is the asymptote. So the asymptote is a horizontal kind of limit to the data. So you can see that it's about 250. I think I said 200. Yeah, so I said 200 as a starting value. So you want to just give it an estimate that's close for the program to be able to estimate the values correctly. Then B, we said, was the displacement on the x-axis. So there doesn't seem to be much displacement. The earliest observation seems to be a little bit ahead of 0. So I estimated that as 2. And then the growth rate is kind of like the slope. So if you think of this as rise over run, I said that the growth rate seems to be about 1/10. So with those starting values, I input that into this function, and then this gives me the final estimates after optimizing. So this is saying that the final asymptote was actually around 203, so very close. This was saying that the displacement on the x-axis was 5 and not 2, and then this is saying that the growth rate was about 0.159 and not zero point 0.1. And now finally, let me plot the actual model fit to the data and show you the fit statistics. So now you can see that the Gompertz model, which is sigmoidal in shape, much better fits the tumor cell growth. So you see that it's capturing the rapid growth in the beginning and also the asymptotic leveling off towards the end, and it gives me the equation with the final parameter estimates, and now our variance explained in the R squared is 0.88. So it's very close to 1, and you can tell just by how close the points are to the actual model that the model is much better capturing the population growth for tumor cells. Alright, so that's it for this video, and thank you guys for watching.